Hello, good morning, everyone. We are in the track 3, paper presentation track. I am Harshavardhan. I will be the moderator for this session. And the first presentation that we have now is a presentation from NXP and Siemens EDA together in the area of clock domain verification. And the title of the track is Accelerating Clock Domain Crossing Design Verification Closure with Supervised Data Retrieval Techniques. And coming from authors Manjunatha, Srinivas, Arpita, Inayat, Jagdish, Chandan, and Abdul. Thank you, team. Let's listen to the paper and we'll come back to the questions at the end of the session.
Hello, everyone. Welcome to the presentation, Accelerating Clock Domain Crossing Design Verification Closure with Supervised Data Retrieval Techniques. My name is Manjunatha, and I'm Application Engineer for Design and Verification Technology Products at Siemens EDA. In this paper, we have worked with a very knowledgeable set of design engineers, Inayat, Arpita Agarwal, Jagdish, Patil, and Chandan Kumar from NXP Semiconductors, and my colleague Moyeen Abdul from Siemens EDA, wherein they have helped in sharing their valuable inputs to write this paper. In this paper, we present how one can achieve faster clock domain crossing verification closure, leveraging the superior data analytic techniques. We have closely studied how the CDC results analysis and setup process can be automated with CDC data mining and machine learning features to reduce the designer effort and time to verification closure. Introduction. Clock domain crossing CDC verification is a growing problem. Nowadays, digital design specifications have more number of asynchronous clocks based on complex design requirements. The increase in the number of asynchronous clocks results in clocking issues and raises the necessity to verify the asynchronous data stability between two different clock domains. And this is done with the guidance of design and verification process called CDC, Clock Domain Crossing Technology. Now, the problem becomes challenging when analyzing millions of CDC paths reported by the CDC verification solution. This is a growing problem when handling different levels of design hierarchies with IPs, tiles, subsystems, and SOCs in a design. Without proper help and setup from the CDC static verification tools, analyzing the huge CDC data at busy schedules of the project milestones is a time-consuming and tedious task for the RTL design engineers. CDC setup challenges. CDC verification process is highly dependent on the quality of the CDC setup. So this slide captures the flow and methodology of how the incomplete or bad CDC setup specification leads to the CDC analysis to produce inaccurate CDC results and noise. This will further increase the effort of waiver specification and the CDC results review, which directly impacts the CDC sign-off schedule. Incomplete constraints lead to misleading CDC results and thus failure to drive the design by the specification. The complexity further increases if the design is integrated at if the design is verified at various levels of the hierarchies. With experience and with increasing design knowledge, engineers learn to write better constraints for a particular design. But initially, we need to get some guidance from the CDC analysis to reduce this effort. CDC setup challenges. CDC setup is a starting point when preparing your design for the CDC analysis, and this includes configuring the design with the required information such as clock groups, resets, port domains, stable constraints, constants, gray coded and mutually exclusive constraints, etc. The lack of these information during the CDC setup affects the various parameters such as CDC signal to noise ratio, increases the effort in results review, waiver specification, misleads the design from being operated in a valid functional mode, and may even put down the design to set up CDC analysis for higher performance and incomplete analysis. For example, there can be crossings in the design between a few clock pairs which are expected to be synchronous, but initially there are no such constraints provided, and the user is presented with a large pool of CDC data crossings to explore and decide upon. Such cases will require setup and constraints fixes, and this is achieved by investing a lot of time and effort to reach a reasonable state for the detailed analysis of actual CDC issues in the design. CDC issues having common root causes. In a CDC design verification, the users face a major challenge in cleaning the most common CDC design problems. That majority of the time contribute to more than 50% of the total number of CDC crossing paths. The following are some of the most common and highest severity CDC cases observed predominantly in the design. Single bit control data unsynchronized crossings, multi-bit control data unsynchronized crossings, data mux based synchronizer crossings or synchronizer enabled data crossings, combinational logic before valid synchronizer path crossings, asynchronous reset unsynchronized crossings. So in this paper, we have focused mainly on these types of CDC crossings to get inputs from the CDC data mining techniques, where CDC analysis can assist users to identify the root cause for these CDC violations and errors. Typically in the design, we may have lakhs of such crossings reported. Analyzing and resolving such a huge number of CDC crossings is a tedious and time-consuming task unless designer does not know the common root cause for all such crossings. Solution to CDC setup. This slide captures the flow and methodology of how the complete or good CDC setup specification leads the CDC analysis to produce accurate and expected CDC results. This will reduce the effort of waiver specification and speed up the CDC results review, which directly improves the designer's productivity and decreases the CDC sign-off timelines. The data mining and machine learning feature not only analyzes the CDC results to recognize patterns, but also uses this information to provide the CDC setup recommendations. Before analyzing the design for CDC problems, the best practice the user can do is to start with a cleaner design constraints setup. This ensures in the specification of the designer's intent, optimistic CDC results output, exposes real scenario CDC bugs, and most importantly, helps in faster CDC closure of a design. Solution to CDC setup recommendations. In the following table, we have listed some of the crucial and requisite constraints used during the CDC analysis. Corresponding to these constraints, we have captured a high level of description of what impact would these constraints have on the CDC analysis of a design. Also, we have shown as a solution, utilizing the supervised data mining techniques, what are the CDC setup recommendations that can be provided to help the users to resolve the unsynchronized crossings. In the upcoming slides, the results section contains the effect of these suggestions on the CDC analysis time and effort. For example, clock grouping constraints directly impact CDC analysis. Clock group partitions all the clocks in the design. More number of clocks directly impact the number of CDC paths. And the solution and the CDC setup recommendation here would be to suggest potential synchronous clocks in the design. Port domain constraints specify the clock domain characteristics for the DUT primary ports. This impacts the design's internal and external crossings. The solution and the CDC setup recommendation here would be to suggest potential port clock domain information. Similarly, we have stable signal constraints, mutually exclusive signal constraints, and synchronizer enabled signal constraints that impact the CDC setup and analysis. And we have captured the solution and the CDC setup recommendation for all these. Results. As discussed in our previous slides, the most common problematic cases of CDC paths in this paper, we have showcased how the data mining and machine learning feature capabilities during the CDC analysis helps users provide potential suggestions for the CDC constraints and has resulted in a major reduction of unsynchronous crossings detected in the design. In our research, we have extended our trials and experiments to a real design, and the observation is done between two cases for the same design. Case A, CDC analysis of a design without applying potential root cause, and case B, CDC analysis of the same design with applying the potential root cause obtained by the CDC data mining techniques. The combo logic crossings are impacted by the mutually exclusive or stable constraints. The no synchronizer and multi-bit crossings are impacted by the clock grouping and stable constraints. So, results and statistics for case A and case B analysis of the same design as we discussed previously. The reduction in CDC violation demonstrates the efficacy of the data analysis features in analyzing the data and providing setup guidance. In this table, case A suggests the violation count without applying potential root cause, and case B suggests reduction in violations after applying potential root cause. For no synchronizer violations, we see a percentage decrease of 53% in the violation count from 2,526 crossings to 1,189 crossings with the utilization of supervised data mining suggestions. Similarly, for multi-bit crossings, we observed a 37% decrease in the violation count and a 94% decrease in the combinational logic crossing violation count after utilizing the data mining suggestions. So the outcome is from the CDC results obtained after applying the potential root cause and suggestions, we were able to reduce the CDC verification closure time for the design from 2 weeks down to less than 1 week. The solution to CDC issues having common root causes. Often the CDC violations may have a common root cause, but designers may spend large effort to review and correlate the violations. With the help of machine learning techniques, CDC analysis assists users in automatically identifying the root cause for the CDC violations and errors. For example, multiple sources of combinational logic violations may have common RX. This is reported as possible unexpected combo logic violations in the design. Similarly, the same source of asynchronous reset can affect different fan-out cones, resulting in a huge number of asynchronous deassertion violations in the design. And all the multiple RX destinations can be fixed by fixing one single source in the design. More results and statistics. We have carried out a few experiments on more live designs of various design sizes. And the following are the results of our analysis and investigation. The tables below capture the design information for sample design 1 with stats showing CDC setup and constraint suggestions as suggested by the CDC data mining techniques and the impact on the CDC violations. And the other table depicts reduction in the CDC violations due to application of data analytics. So looking at the table, we have around 6 potential synchronous clock pairs as suggested by the data mining techniques. Similarly, around 7 potential stable constraints, around 2043 potential enable control constraints for the demux crossings, around 63 common reset source suggestions. So on an average, there are around 2047 related violations that are getting impacted by these setup constraint suggestions. So total dependent violations on the 63 common reset source suggestions are around 1,28,961 crossings. So the violations count without applying potential root cause is around 6,26,266 crossings, but with applying potential root cause, we see a reduction in the violation to 4,85,552 crossings. So this indicates a percentage decrease of 65%. More results and statistics for the sample design 2. So we see here, we have around 3 potential synchronous clock pairs, 12 potential stable constraints, 0 potential enable control constraints, and 8 common reset source suggestions as suggested by the CDC data mining setup recommendations. So on an average, the related violations are 495 crossings. Total dependent violations on the 8 are total dependent violations on common reset source suggestions are 3,959 crossings. Violation count without applying potential root cause, we have around 57,511 crossings. And after applying the potential root cause, we see a reduction in the violations to 8,500 crossings. So this indicates the percentage decrease of 15% in the total number of crossings. Advantages. So we can see improved debug and analysis, the causality reporting of the most common failure root causes, and improved CDC results debugging capabilities. We have high quality of results and reduction in the noise. So the application of supervised machine learned suggestions has resulted in a major reduction of unsynchronized crossings. This helps, so we see a setup recommendation by the CDC data mining techniques. So this helps in the cleanup of designs with a better optimized setup and achieve expected results. It helps in faster CDC closure, improves the designer's productivity, and reduces the CDC analysis time and effort. Helps review the root causes based on the order of impact on the CDC violations and take action for the bulk resolution. So to conclude, the utility of machine learning and data mining techniques automate the CDC setup process, reduce the redundancy of CDC verification results review, and reduce weeks or months of intense designer verification effort to sign off the CDC clean RTL. Overall, up to 50% of violations on average are resolved by just employing the initial suggestions from the CDC analysis data mining techniques. From the below table, we can deduce that how the constraint suggestions could impact the reduction of most common problematic CDC violations in the design. Thank you.
Thank you for your presentation. It was good to learn you adopting ML technologies for CDC verification. So I got a few questions here to take, right? I think the first question is, you quoted this as supervised learning. What part of it is supervised? Are you learning from your previous chip data to basically identify potential root causes in the current chip as a derivative, or you are basically doing data mining within the current chip results?
We are doing data mining in the current design only.
Okay, so supervised specifically, any reason? What exactly is supervised here?
So cannot go into details of the algorithms over here. But yes, we are using the data from the current chips. For example, I can say.
Okay, and the second question is also on, is there any validation done on the root causes applied, or we automatically applying what the tool is recommending, or it's just a guidance?
No, yeah. So the flow is that we find out the root causes and suggest it to the user, and it's up to the user to apply it to the design. So once reviewing it.
It is only a suggestion, basically.
Yeah, got it. And any quantification on the impact of user waivers? Normally, CDC verification, a lot of people apply waivers quite a bit. So you're applying more constraints guided by the ML right now. So any indication of reduction of waivers in your methodology and guided by ML?
Okay, thank you. So the use flow is to use this feature before in the fresh design, before you have written any constraint for your design or any waivers for your design. But if you have used waivers in your design, we will consider that. We'll see after applying waiver how many current violations the design have, and then we'll do analysis on that. So that's how it works. So yes, it considers waivers, but it is meant to be used before any constraints or waivers have been developed for the design.
Good. One other question was, is this feature applicable and available for netlist level CDC verification?
No, this is not available for netlist level CDC verification as of now. For RTL.
Right. Yeah. Another similar question on methodologies, is it also applicable for users who is using hierarchical flows?
Yes, it is perfectly available for users using hierarchical.
Okay, I think we have 5 questions. I think we are good. Thanks for answering all of them.
Thank you.
Thank you. Thank you for your time.
Thank you.